All right, so let's talk about the next step, which is 3.2.1, the file input. This section is actually pretty much a refresher of assignment 0. So a lot of the tricks we're going to use here are straight out of assignment 0 when you had to read from an input file. So the only trick, the new thing we're doing is they already have a joint class defined for you, and you're going to be using pointers to memory locations to sort of save the joints as you're reading them from the file. So they're saying new joint, so that's going to carve out some memory in your RAM, and this star joint is the address to that memory. So as soon as you carve out the memory, you're going to add in data to that memory, and then you're going to save the address to that memory into a joint vector that you'll work with. So first off, let's go take a look at the load skeleton function. Let me see here. So here we are. We can get the matrix stack out of the way. That is all good to go. Let's go ahead and do a build really quickly. Make sure we can still build. I haven't tried that yet. Excellent. Oh, and by the way, I forgot to show this when I started this recording, but if I hit the play button, you can see that we are basically where we left off in the last video. So, oops. What is that doing there? I think I was playing around with this code offline. But yeah, I have a sphere there. I should go delete that. Let me pause and delete that really quickly. Okay, sorry about that. Just wanted to show that we're basically at the same point from the end of the last video. I am going to show how to draw spheres in this video that will be coming up soon. So anyways, let me see, what was that fun? We want to go to the skeletal model class and look at the load skeleton function. And it's telling us that we're going to get the correct file name, and then it explains this .skel format. So hold on one second, let me get there. So we want to go to the skeletal model.cpp, and we also want the skeletal model.h. Great. Let's go to the .cpp, and the skeletal model load is going to call load skeleton function. If we scroll down, here is the load skeleton function. So load the skeleton from file here. Okay, so let's look at the file for a second. If we right-click on the project name, right-click. Ooh, it's taking a minute to load. There it goes. We're going to do a reveal in File Explorer. Open folder in File Explorer. There it is. Okay. And then this folder right here, data. Double-click on that. And these are our input files, but make sure you don't get do not select the ._. Want to scroll down, find model1.skel, right click on that, and let's open that with Notepad. I had opened on my other screen here. That's okay though. So I just want to take a moment and explain this file format in case if it's not making sense. When you read it, it should make sense when you read it though. Just take some time to study what it's saying. So we have each line containing values separated by a single space, which is helpful for us. And it's telling us that these first three are going to be coordinates, and the coordinates are going to be a transformation. And then the last one is going to be the parent-child relationship index sort of thing. So what does it call it? The final field is the index of its parent. So when it says index of its parent, it's talking about what position. So this guy is saying position 1 is right here, right? Because this will be position 0. And this guy is saying 0 is its parent. So 0 is this guy's parent. -1 does not exist. So this guy is the root. And then this guy, its parent, is position 0. This guy's parent is position 1. This guy's parent is position 0. So that's that guy again. This guy's parent is position 2, which is this guy. We'll draw it out in a minute, but we just got to get these read in correctly. So let's attempt to do this. So the first thing I want to do is I want to get root joint. The next thing I'm going to do is we will basically create joint and then make root joint point to itself. We're going to also set root joint, and yeah, so let's see here. Let's check let's check the header file for what we have to work with for this file name. Like, what do we have available to us? So back in the header file, at the top you have all these includes, and we can see we have vector, we have ssstream, which I am going to use, we have fstream, which I'm going to use. I'm not going to use iostream, but you could if you wanted to. But yeah, so I'm going to use fstream and ssstream. So the first thing we're going to do is we are going to create a ifstream for the input file, and we're going to open using that file name. The file name provided to us in the function arguments, this file name. Okay, and then we're going to check if file name is open. Then we're going to do some stuff. All right, and we're going to do this stuff in particular. Great. So if get line from the input file, we're going to save this in a string. Like that. So if we can get a line, then the file is not empty, and then that means we can start to parse this thing. So I'm going to use string stream, call this SS, and this is code that we straight up saw in assignment 0. So ss.str from the line, and this is going to allow us to work with the tokens that were in that line. And we're going to take out the first 3 coordinates. So if we use vector 3f, and we'll call this core. And so for core 0, that will be our x. Core 1, that will be our y. And for core 2, that will be our z. And then our last one, we got to save our index, and that is going to be an integer. So int index right there, index. Okay, so we're going to get the line, and then this will be coordinate at position 0, coordinate at position 1, coordinate at position 2, and then our index. And that's a cool trick we saw in assignment 0. Great. So next up, we're going to create the joint. Tap these guys in. So this is going to be our line of code that they give us. Joint star, or joint star joint is equal to new joint. So type joint, and it's a pointer joint, is equal to new joint. And we just carved out some memory. And then what we can do is we can access, I actually like the star to be like that. We can access, using this arrow operator, we can access the properties of that joint pointer. using this arrow, so the dash greater than sign. We're going to get the transform, and that is going to be equal to, and if we go and take a look at this joint class, so let's look at joint.h. We have transform, which is of type matrix 4F, and we have some other functions we can access, but and we have children, which is a list of its children. So transform is going to be a matrix for F that is actually going to be a translation using our coordinates, like that. And this is valid because if we go into VecMath and we look at matrix 4F, we see that we have the translation. Let's not look it up manually. Let's do it this way. Right click on it, go to definition, and here it is. So this is exactly what we wanted. We want to take our vector 3 translation and put it in a matrix at those positions. So this function does it perfect for us. It's returning that matrix. So this is exactly what we want to use. Great. We'll close that. And so that handles our joint transformation. Next up, we need to set the root for this root joint. And so joint children dot pushback joint. Now, when I did this code at the time, I thought this is what I had to do. I'm starting to think this isn't necessary. You can just leave the children of the joint blank. But later on I realized, oh, I do have to go through each of the children, and if I go through the root joint children, I'll be in an infinite loop because it's saying the child of the root joint is the root joint. So later in my solution I account for this. This is something particular to my code. If you want to go a different route, I would simply skip this line of code. Don't make the root joint child of itself. That's probably not necessary. And actually, I think it would be easier because then if you're trying to loop through all the children of the joints, you'll see that the root joint has no children, and you'll be done. But yeah, I'm going to stick to this because that's what I did 2 months ago. Okay, anyways, and then we're going to set the root joint. So the root joint on skeletal model, right? Yeah, there's a private member called, it's a pointer, and it's called m root joint. So we're going to set that. M root joint is equal to this joint, because this is our very first guy that we have read from our input file. And then next up, we are going to, on our list of joints, we're going to push back the root joint, because we need a list of all the joints. Great. Looks good. All right. And then now we're going to be reading this first line, but we need to read the rest of the line until we reach the end of the file. So we're going to be basically doing something pretty similar to what we did on the root joint, but instead of if, we're going to do while. While we can still get a line, we're going to do this. Yep. And we're going to do this. Looks good. And we're going to do this, which is fine. It's going to overwrite our coordinate, overwrite our index variable. That's all good. And then we're going to create the joint, which looks good. And then we're going to do a transform, which is the same code. Looks good. And then we're going to not do this. And we are going to push back our newfound joint. Add joint to vector. And then we are going to attach to parent. All right. So attach this joint to its parent. So what we're given, so like let's say we're at this guy right here, and we're given this index, and this is the index of the parent. And it is the index of the parent in our vector of joints. So it's giving us the index of the joint in this vector that is its parent. So we basically need to look up in the vector of joints and attach this joint to its parent as a child. All right, so we need to attach this child to its parent. I'm hoping that makes sense. Using the index we just parsed, we're going to access the joint with this index. We're going to access its children, and we're going to push back on its list of children this joint. All right, so that is pretty packed in there, what I'm trying to say. But basically, we're saying, as we go through and we attach things, this guy is 0, and then this guy is the child of this guy, right? This guy is the child of this guy. That's what I was saying earlier. Yeah, I encourage you to draw this out. I did draw this out, and I'm willing to show what I ended up drawing. So let's see here. So here are my notes. I created this table. So this table is exactly the input file. All right, and then I kind of used an X to mark who is going to be the child of who. But then I also ended up drawing this sort of diagram. So I drew 0, and this is index 0, which is this guy. And then I drew the indexes of the guys that say their parent is index 0. So number 1 says its parent is 0, so there's number 1. Number 3 says its parent is 0. Number 12 says it's 0. And then on the left here, this is showing the indexes. And I just sort of drew this, this tree here. Yeah. All right. So I encourage you to think this through and think about how this is all going to work out. The other thing I want to point out is it looks like from the input files that are given in the example, so back in this data folder, model 1, model 2.scale, model 3.scale, model 4.scale, if you go through and check these, it looks like you're pretty much guaranteed in the input file, you are guaranteed that you are going to have an index for the line you're currently reading. It's going to be an index pointing to something you've already read, right? So this guy won't say number 7. We're on number 2 and he's saying, oh, my parent's number 7 way down the list and you haven't read it yet, so you're going to have a problem. It looks like you don't have to worry about that problem. It looks like the input files are guaranteeing that you're always going to have an index of something you've already parsed, and it will feed them to you in this order. So you're not going to get them out of order. It's going to give them to you in order. And if you look at this list, it is sort of ascending. So -1, 0, 1, 0, 2, 4, 5, 6, 2, 8, 9. So we do go backwards, and we do get 8, but we never go forward. So we're at position 6, and it's not asking for 10. It's asking for something that's already happened, which is 5. So I just want to stress that could be a problem. But it looks like you're guaranteed that you're going to have an existing parent every time. But yeah, so it takes a lot of careful thinking, and if you couldn't get this on your own, I understand. It took me a long time just to get that right, or even to sort of extract that that's what they want you to do from that. Okay, great. So other than that, that is the end of our load skeleton function. That is pretty much all we need. Just kind of skimming through the notes really quickly. Yeah, we're done. Great. So next up, we are going to look at drawing stick figures. Now, this is where it's getting pretty dicey. But what they're giving you is they're saying in the draw joints, they want you to draw spheres at each joint position. All right. But before we do that, let's sort of look at this draw sphere and what we can do with our matrix stack that is now implemented. And then the bones is going to be after that. But let's just look at drawing spheres first and getting used to what's going on. All right. So let's come down here. And so in our skeletal model.cpp, there is the draw joints function. And I have here some code that I already wrote. And let's leave these two commented out. So in your draw joints, we can go ahead and add a sphere. The GLUT solid sphere, radius, slices, stacks, just straight out of, this is a line of code straight out of the recommended code that is in the instructions. Let's go ahead and hit play on that, and let's see what we get. Okay, so I put it all down on my other screen here, but if I bring it up to the top, you can see that we have a sphere at the origin, and that is looking pretty good. So let's start to look at what our matrix stack is going to do for us. What we'd like to be able to do is move this to the position of a joint. So let's talk about moving it. So I have here this commented line of code. Click stop, close that. Let me open this for a second. Okay, so I have here this commented out line of code. Let's uncomment this and uncomment this. And I have I'm pushing onto the matrix stack a translation. And then I have this line of code, GL load matrix F, and we're getting at the top of our matrix stack. So let's put these other guys to 0, and let's run this. Might take just a minute to load. All right, so now we have our sphere translated over here. What I encourage you to do is try to draw a sphere at, draw multiple spheres at each tip of the axes here and also one at the origin. So go ahead and pause the video and give that a try, and then I'm going to discuss what's really going on here, because you might start running into some strange things that are happening. Okay, I'm assuming you gave it a try. Welcome back. So let's take a look at this. So if I push onto the stack and then I draw a sphere, and then I just copy this line of code, and then this time around I'm going to do this guy. What I would expect is I have a guy at the tip of the red axis, and then a guy at another tip of one of the axes. Let's see what we get. And we do not get that when we actually look at what happens. Instead, what we get is, think of it as like as you push things onto your matrix stack, you're pushing more and more translations on. So we got a sphere above this sphere, which is not what we wanted. We want to be able to get back to this guy. So there is a couple of ways of doing that. One of which is, okay, we can clear the matrix stack, and let's go ahead and look at this option. Clear. And then we'll push on our transform and draw it. This is one way we can get what we want. Give it a minute to load. And actually, I don't even know. Oh, so if you tried to clear and then you couldn't get the sphere to draw, what you've done is you've actually cleared off the camera transformation. So in graphics, you have, like, you're in your world coordinates. You need to transform to the camera, and then you need to transform from the camera to where you want your object to be drawn. And if you clear off that camera matrix off your stack, nothing you draw is going to show up. You're not going to know where it's at. So yeah. And if I close that and we scroll up, you will see that we have, there it is. We're pushing onto the stack the camera matrix. So if you clear the stack, you sort of did a number on yourself and you've lost the camera matrix. And I don't think you can bring it back because the camera matrix is being supplied as an argument only on the draw function. So there's not really a way you can bring that back in once you clear it. So instead of clearing, let's just do a pop. So we're going to pop off the previous guy that we had, and we will see what we got. So just really quickly, I don't think I touched on this earlier, but let me just quickly go back. Where am I going back to? The matrix stack.cpp. Let's take a look at this for a second. So this is pretty ingenious, the pop and the push and what we have going on here. So this is worth bringing up. What's a good way to explain this? I think I want to go to Excel. All right, so I have here a simple 3x3 matrix, and it's the identity matrix. Ooh, nice try. Almost did a 4x4. Okay, so we're going to apply a transform to this. So that's going to be equal to this guy. Actually, hold on a second. I'll delete this. Let me pause the video and make this example, and then I'll resume. Okay, we are back, and I have a little bit of an example to explain what is going on here. So we have matrix A, which is the identity, and then we have matrix B, which is just some, doesn't matter what the matrix is, and then we're going to do A multiplied by B. So I have here the Excel formula for multiplying those two matrices, and this is our result. And then down here, I'm using the Excel function to get the inverse of matrix B. And we know from linear algebra that if we multiply matrix A times matrix B, and then we multiply the B matrix with its inverse, you're basically multiplying the identity by the identity. And because the inverse multiplied by the matrix is going to give the identity. And we can see that that looks about right. But here's a problem you can run into. So I'm going to add on a new matrix C, and this C matrix is a little bit different. And we're going to do A times B and then times C. So now we've got this guy multiplied by our new C matrix. And this is a little bit like what we're going to be doing in our project, which is we're going to have this matrix that gives a translation, and then we're going to multiply it and get another translation. We're stacking these translations together. We're just kind of piling them together into one matrix that will be our transformation matrix. It'll do a rotation, scale, transform, translation, I mean. So this is a little bit what we're going to be doing, but another thing we need to do in our project is we need to be able to go back to what we had before. We need to be able to go back to A cross B. And so if we do this, if we do it using the linear algebra, this little trick, if we multiply it by the inverse, we can take it back off. And if we just kind of compare, this guy should be equal to this guy. So let me copy these values and bring them over here so it's easier to see. and I want to copy just the values. They are not the same. We have this weird value right here. What is that? So let's increase decimal. Oh my gosh, 10 to the negative 18. We have a tiny, tiny little bit of a value when it should be 0, but it didn't go back to 0 when we multiplied our inverse. And then additionally, when we go back to AB using multiplication as our method for getting back, there's this strange value that popped up. And what you can call this value, what you can think of this value, this strange glitch that appeared of being very, very close to 0 but not quite 0. This is actually called floating point error, and this is a drawback of doing it on the computer. So the computer can only hold so many decimal places when it does its computation, and as you chain these multiplications and then you try to undo them with more multiplications, this error is going to start to grow. You're going to start to drift away from what the actual original value was, the actual original matrix. You're going to drift further and further away as you chain more and more. So the way we're getting around this, the way we're able to completely get rid of floating point error is we're not going to do this. We're not going to pop off a matrix by multiplying by its inverse. We're not going to do that. Instead, what we're going to do is we are going to simply pop back. And then each time we push on, we're multiplying them. So we're taking the current back and we're multiplying it by the new guy, and we're pushing that on. And then as soon as you pop that new guy multiplied by the back, you're now just left with just the back as it was before. We're not going to do any of this inverse matrix nonsense. So that is pretty ingenious way of handling that floating point error from growing. So anyways, back to the thing at hand. So we have the pop, and the pop is going to allow us to take off the most recent thing we pushed on, which was this translation. And then now we're going to push on a different translation, and doing it this way, we should have a sphere at two different tips of our axes. If I hit play here. Okay, and there it is. So this is looking good, but this is one way of doing it. So what we saw before was we did our first translation, which brings us here, and then when we did our second translation was just going straight up. And instead of going straight up from here, it actually went straight up from here. And so what you can really think of what's happening is you're sort of moving your cursor to here. Your cursor is always the center of the world, and you move your cursor here and you can place it, and then you move your cursor here and you can place it. So another way of getting our sphere here is if we come here, place our guy, come up, and then come over, and then place our guy. So that would be the equivalent of, once we're here, we're going to come up in the y direction, 1, but we're also going to subtract 1 from the x direction. So that will be an equivalent way. So instead of doing this pop, let's take that off. We're going to do a -1 in the x-axis. -1 in the x-axis. And we'll hit play. We'll wait for that to come up. And there we go. We're left with the exact same thing we saw before. But this time, just think of it in steps. We're moving our cursor here, popping in a circle, and then we're moving our cursor here and here. So we're going straight there all in one step and then popping in a circle. But notice that we're drawing this circle relative to this guy. So these guys are sort of in a hierarchy. Instead of undoing all the work we did, and then we're going here, and then undoing all the work we did, and then we're going here, we're doing it in a hierarchy. So these guys are drawn in a relationship to each other. And that is going to be something that is important to understand when we're drawing our bones. And I do have an example demonstrating that later on. But yeah, so let me pause the video, and we'll come back and we'll look at how we're going to draw the joints for each of the joints in our hierarchy.